All right, so you're going to want to hear this. There's a new paper out of Google Research, and it's making a pretty wild claim that we've basically been looking at deep learning all wrong. They're saying that just stacking more and more layers, the very thing that defines modern AI, has some serious, fundamental limits, and that to really move forward, we need to start thinking in a whole new dimension.
And listen, they are not pulling any punches. The title of the paper is literally Nested Learning, the Illusion of Deep Learning Architectures. I mean, wow. This isn't just some new model they're proposing. No, this is a full-on challenge to the entire way of thinking that got us everything from AlexNet to the giant language models we have today. They're basically saying what we call deep is, in reality, kind of flat.
So what's the big problem they're pointing at? They call it the LLM's amnesia. And they use this great analogy from neuroscience, anterograde amnesia, which is a condition where you can't form new long-term memories. They argue that large language models are exactly like this. They have all this knowledge from their pre-training, that's their distant past, and they can use the immediate context you give them in a prompt, that's their short-term memory. But there's just nothing in between. They can't actually learn something new and have it stick.
Hold on a second. An illusion? I mean, come on. Let's be real here. These amnesiac models are crushing state-of-the-art benchmarks. They're achieving superhuman performance in some areas. We're seeing these wild emergent capabilities pop up that we can't even fully explain. Calling all that success an illusion feels a little over the top, doesn't it? Are we sure this is a real problem, or is it just a fancy new name for something that just, getting bigger and better models is already fixing?
That's a totally fair point, but the paper's argument is that just scaling up is like building a taller, more fragile building on a flawed foundation. It just makes the core problem bigger. So, to find a real solution to this amnesia problem, the researchers did what a lot of great innovators do. They looked for inspiration in the one system that has absolutely mastered lifelong learning, the human brain.
And the insight they pull from this is just beautiful. Think about it. The brain doesn't run on a single central clock. It uses all these different frequencies, brain waves, from the really slow delta waves up to the super fast gamma waves. It uses these different speeds to process and lock in information on different timescales. Some things are learned and updated instantly, while other deeper knowledge gets reorganized slowly, over days or even weeks. That multi-speed update process, that's the magic trick.
Okay, look, the brain analogy is nice. It's poetic. But I'm always skeptical when we start talking about neurophysiology. It's a great metaphor, but it's rarely a practical blueprint for AI. The brain is wetware. Our models run on silicon. They're fundamentally different beasts. So how do you take this abstract idea of different frequencies and turn it into actual code? What's the algorithm? I want to see the math, not just the metaphor.
You got it. Let's get into the math, because that's where this gets really concrete. The paper takes that brain-inspired idea and formalizes it into this new paradigm they're calling nested learning. And the core idea is simple but powerful. Stop thinking of a model as just a stack of layers and start seeing it as a system of learning modules, basically models within models, that are all updating at different speeds.
So this definition right here is the heart of it. Nested learning, or NL for short, sees a model as a set of nested optimization problems. You've got different levels, and each one has its own update frequency. Some are super fast, some are incredibly slow. And here's the kicker, the paper's big aha moment. They argue we've been using simple two-level versions of NL for years, we didn't have the language or the framework to see it that way.
And this is just a brilliant example of what they mean. Take something every ML engineer knows, gradient descent with momentum. We usually just think of it as one single thing, right? But if you look at it through the NL lens, you realize it's actually a two-level system. The outer level, the slow one, is the main update to the model's weights. But the inner, faster level is the momentum term itself. It's like a tiny little learning system that's constantly learning from and compressing the recent history of gradients. It's been hiding in plain sight.
Exactly. This diagram from the paper just nails it. On the left, you've got the standard, flattened view of deep learning. It's simple, but it hides all the interesting dynamics. But the nested learning view on the right, it makes it all transparent. You can see the different levels of optimization, the different flows of information. It's not just one big monolithic calculation anymore. It's a whole hierarchy of learning systems, each dancing to its own beat.
All right, I get the framework. Decomposing an optimizer is clever, I'll give you that. But the real acid test is whether this new lens gives us any useful insights into the king of the hill right now, the transformer. So, how does nested learning see a transformer? Is it just another one of these so-called flattened systems?
That's exactly what the paper says it is. And this is really the core of their whole critique. When you look at a transformer in NL terms, it's a dead simple two-level system. On one hand, you have the attention mechanism. That's your super high-frequency part. It changes its calculations with every single token. On the other hand, you have the feed-forward network, the FFN. Its frequency is incredibly low. It only gets updated during pre-training. And that's the problem. This massive, gaping chasm between the two. There are no medium speeds, no intermediate learning. And that, they argue, is precisely the architectural reason it can't truly consolidate new knowledge.
So if the transformer has this, let's call it a fatal frequency gap, what's the solution? Well, this paper isn't just theory. They didn't just point out a problem and walk away. They actually went and built a whole new architecture from scratch based on these nested learning principles, and they call it HOPE.
And this comparison here says it all. On the right, you've got that simple two-level transformer we were just talking about. But check out HOPE on the left. The big innovation is something they call a Continuum Memory System. Instead of one giant, slow-moving FFN, it has multiple feed-forward layers, and each one is explicitly designed to update at a different frequency. It creates a whole spectrum of learning speeds, filling in that huge gap the transformer leaves open. The goal here is true, multi-scale, continual learning.
A continuum of memory. You know, it sounds elegant, but my practical engineering alarm bells are going off like crazy. This immediately brings up a whole checklist of problems. First, is this going to cause a massive increase in computational overhead? Second, is it a nightmare to train and tune all these different frequencies? Third, are we talking about a tiny marginal gain in performance in exchange for a huge leap in complexity? And you know, the million-dollar question, does this actually solve catastrophic forgetting, or does it just put a Band-Aid on it?
Those are 100% the right questions to be asking. A beautiful theory is one thing, but rubber meets the road performance is everything. So the only way to figure out if this is a genuine revolution or just a very complicated evolution is to look at the numbers, to check out the results from their experiments.
Okay, so let's start with the 1.3 billion parameter models. And honestly, the data here looks pretty promising for HOPE. Let's look at that last column, average accuracy, where higher is better. HOPE clocks in at 57.23. That's a really clear win over Transformer++, which is way down at 52.25. And it even manages to edge out a very, very strong competitor, the Titans model, which is at 56.82. For a brand new architecture to come out of the gate like that, well, that's a very strong signal.
A strong signal. Yeah, I'll give you that. But it's not a knockout punch. Not even close. If you go back and look at that table, specifically the LMB perplexity score, that's a core language modeling metric where lower is better, the Titans model actually beats HOPE, 11.41 to 11.63. So HOPE wins on one metric, but loses on another. This doesn't scream revolution to me. It screams trade-offs. And the real question becomes, is a tiny bump in average accuracy really worth all this extra complexity we were just talking about?
You know, I think we can both agree on this point. Whether or not HOPE in its current V1 form is the ultimate answer, that might not even be the most important part. The real contribution of this paper could just be the shift in perspective. It gives us a whole new language, a new mental model for thinking about these systems. It's pushing us to move beyond just asking, how many more layers can we stack, and to start asking, how can we compose different learning systems that operate on different timescales?
Exactly. And that really leaves us with the billion-parameter question, doesn't it? Is this nested learning paradigm the key that's finally going to unlock truly lifelong learning AI? Or is it a fascinating, beautiful theory that's ultimately going to crumble under its own weight and complexity when we try to scale it up? This paper has given us a really tantalizing glimpse down a brand new road. But now, it's up to the whole field to decide if that's a road worth taking.